Starting recording. And by the way, if you haven't noticed, this transcript thing obviously is powered by machine learning as well. So that's quite, it's quite clever, really. Okay, so let me start this. Okie dokie. So obviously this second talk is going to be looking at obviously supervised machine learning techniques, namely linear and logistic regression. Now, the first thing I want to point out is, as you've already asked, Mary, you don't have to be experts at mathematics. Really, the key thing that I would like to emphasize is that it's always worth having a look at the mathematics because it helps you understand how these things work. But certainly from an actual practical standpoint, you're not expected to fully understand exactly how these work, because that would be a little bit unfair. So there is some stuff that you guys have already seen from the talk so far around, like, arrays, matrices, that kind of thing. And these will obviously be explained in due course. But for the most part, there isn't too much expectation on the mathematics part of it. And as Ian has mentioned before, typically the way this goes is we have, libraries and things like that already exist. People have done the maths already. People have implemented it in the most efficient way. So there's no need for us to actually go ahead and do that as well. So obviously we have different types of supervised learning. So I'm not sure how much depth you guys have gone into things like decision trees, but effectively, decision trees are, you look at the data and you effectively make a tree of decisions, hence the name, based on certain features. So if a certain feature is over a certain value, you create a branch off that decision, and then you create another branch for the opposite side of that decision. So, and then based on how a particular data point falls through that tree, decides, whether or not something is a certain class, for example, or a certain group, or the value that is generated from that. Now, the thing that we're going to be looking at now with supervised learning is, with linear regression and logistic regression, is that we know the function that we are trying to model. Okay, so we want to use parameters to dictate exactly our model, as it were. So hence this is known as parametric learning rather than non-parametric learning, which is decision trees. So we're looking at linear regression and logistic regression. So linear regression, and the name, again, I'm not too sure how much in depth you guys have gone into some of the terminology, but regression refers to trying to fit some kind of function as close to the data as possible. And it's generally some kind of continuous output. So for example, you will look at an X and a Y, and you're looking at the relationship between the two of them, so that if you provide an X, you can get a Y value back. And similarly, we can use linear regression to do this, and I'll go through how that works specifically. And linear regression forms the backbone of a lot of machine learning algorithms. And similarly, on the other side of it, if we want to look at, say, a classification problem, all this means is we have different distinct groups, and for a given piece of data, we want to try and predict which group that piece of data belongs into, or that instance in that case. And we can use logistic regression for that. And I'll explain why that works in a moment. Okay, so don't be too scared by the symbols and things like that, but I'll try and explain this as best I can. So obviously, linear regression, we're trying to fit a particular function to some data, okay? And the function that we're trying to fit to the data, and hence the name, is a linear function or a linear equation. So hence the term linear regression. So what we're assuming is that the relationship between our data and our output is some kind of linear relationship, so we can draw a line between them. And so if you remember from secondary school mathematics, you may have come across an equation that doesn't necessarily look like this, but similar, where it'd be y equals ax plus b or ax plus c, something like that. In this case, we're using b for this. And really how this works is, so for a given y, we have as many x's as there are features, and then we also then have b here, okay, or weights in this case, or biases, depending on which terminology you want to use, that are associated with each x. And we also then have a final one on its own. And the idea of this is the linear equation. So it basically describes how can we draw a line in any on a 2D chart. How can we actually draw a line in any direction? And this can be simplified down. So what we're going to say here is that W will be the vector representing all the biases here. And then we end up with this, where we say our equation, or our y, is going to be equal to all of the x's multiplied by all of the weights or biases in this case. I hope that makes sense. Okay, I'll just double check the chat if anyone said anything yet. Cool. Okay, that's all right. So, yeah. So what we have is that's effectively the equation for any straight line. We have some kind of weight associated with an x, and basically all that means is how important that x is to the overall y output. So the key target we're looking to do with linear regression is we want to get our y equation should be as close as possible to the real y data that we have. So we're looking to minimize that difference. Okay, don't be too scared. Okay, so the key thing here is we need a way of measuring how wrong any line that we choose is. So the way we do this is we have two different error functions here. Now, these error functions are actually used very commonly in machine learning anyway, if you're doing any kind of regression analysis. So you'll probably hear these acronyms come up a lot. So MSE being mean squared error and RMSE being root mean squared error. They are effectively the same, just that root mean squared error puts a big square root over everything. And again, don't be too scared by these equations, but effectively what these equations mean is, so for every data point, what we want to do is take the given weight multiplied by the data point and subtract it from the real data. And that basically gets us the difference for every single data point. So what we're looking at doing is we need to know how far off is every data point from its equivalent point on the straight line that we draw. And effectively all that's doing is measuring the difference between the two. If I can make this point options 10. Okay, so if we were to take a line here and we've got some can you guys see me drawing on that? I hope so. Otherwise it'd be a bit underwhelming. So I'm going to put some dots on here, very small, and we draw some line. Okay, what we want to know is what is the distance between each dot and the line that we have. Okay, and the reason that we square it is because some of these dots will be below the line and some of these dots will be above the line. So what this then means is obviously some of these values will be negative and some of them will be positive. So to avoid having where they just cancel each other out, we square everything so they're all positive numbers. So I hope that makes sense. So we do this for every single data point on here, effectively. And our total error is the sum of all of these green lines here, basically. And again, the only difference between this, between RMSE and MSE, is the fact that this one we just square root it. That's it. So there is certain benefits and that to each one, but obviously at the moment it's not too we're not too worried about that. Okay. So linear regression itself has what they call a closed form solution. So this is a simplified solution whereby our weights is effectively the inverse of our data multiplied by target multiplied by the actual final value. So that is effectively the full equation of how we solve it for. So how do we calculate these weights that we need to know? So those are our parameters in this equation. However, doing this is often quite expensive computationally. So I'm not sure if you guys have seen this before, where we put a big O and then some kind of brackets. So all this refers to, this is what's known as big O notation. And all this refers to is how complex is something computationally. That's all it means. So depending on what it is, it can be slower or faster. That's to be honest, me personally, all I've ever used that for. There are other ways of doing this. So, okay, so to actually look at a proper example, this is how we actually do linear regression inside of Python. Okay, so again, we don't actually have to write the mathematics for this. So thankfully, libraries exist that let us do it. So let's assume we've imported our machine learning library, and then we have this linear regression class or function here that we can create. So what's happening here is RGR here is just a short name for our regressor or our regression that we're going to use, and it's equal to linear regression. So that's the algorithm we're using. We then tell our regressor to fit to some data, in this case X and Y. Okay, and this is what our X and Y data looks like. So for this data, what we've done is we've generated some sample data using the following equation up the top here. So we're saying 4y is equal to 2x plus 3 plus a random number, so that we get this nice scattered effect. Because if we just did 2x plus 3, it would just be a perfect line. So we put this random factor in C to make it actually a scattered plot here. And again, all we're doing in this rest of this code is just mostly cosmetic. So all this code does here is it creates the chart you see on the side here. And then we actually want to do the line here. Okay, so if I do that, then we'll see the line that has been created by linear regression. And the way we do this is that, we know what the X range on our chart is going to be, and our Y values are going to come from our regressor. So we're telling the regressor to calculate the coefficient of the lines here. So, and then all we do is we show that chart. So what is happening here is, so we've got our data that's generated by this equation at the top, and our linear regression algorithm has dictated a line. So what it's gone and done is measured all these errors here and effectively adjusted its weights for each one up until it reaches, adjusted its weights for, say, this value and this value until it reaches the perfect, the lowest error possible using mean squared error or root mean squared error. And how we can show how good this line is we've told it right at the end here to print off the regressor coefficient. So this is this value here, and the intercept, which is this value here. Okay, and if you look at the printout at the bottom here, we can actually see those two values. So that first one is our coefficient, and you can see it's 1.937, and that is extremely close to 2, which is what we generated the data from. And our intercept is 3.1, okay, which again is very close to 3. And we can actually see that directly in the chart because our line starts at 3.1, roughly there. So that's how you can see. And all the coefficient refers to in this case is the angle of the line. So if I were to draw a triangle here on the line, let's say in this case, for every 1 that the line goes up, because it's 2x, we're expecting it to go 2 along. So I hope that makes sense. So effectively what the linear regression has determined here is that the angle of the line that's the best is 1.9, and the line should start at 3.1 with the intercept there. So, and you can see that that is very close to the actual target that we started with. So I hope that makes sense. I'll just double check the chat if anybody's okay. So why do we need to find them? Because that is effectively the parameters of our equation. So when we're looking to, we can draw a line here on this chart in any direction, okay? And for each line, they have a different set of parameters. They have a different coefficient and intercept. And the idea is what we're doing with linear regression is we're trying to find the best coefficient and the best intercept that fits this sample data. So which coefficient and intercept produces the least amount of error from this data? And obviously, if we drew a line that just went, for example, straight up like this, that, coefficient, the intercept would be not that, and the coefficient would be 1, because it just goes straight up like that. And so that line would just be y equals x equals 1, sorry. But this line does not fit this data very well. So what's going to happen is that the algorithm in this case is going to measure the error between each of these, like so, determine that that's a lot of error, and effectively then draw another line that say, that might be of an angle like this, remeasure all its errors, and determine that this second line actually has a lower error than the first one. And it will keep doing this until it reaches a minimum. And then this is that line of best fit. So if you've ever drawn a line of best fit on any chart in Excel, for example, that exactly is what you're looking at here. It just does it so quickly now with modern computers that, we don't need to worry about it. And again, for this, we're not expecting to actually work out these values. We're just going to create a model that knows what these values are. Okay, so this is how it's also done if you wanted to actually do the maths for it within Python. And again, I'm not going to spend too much time on this, but you can see here that the values here are very similar. So we get an intercept of 3.1 and a coefficient of 1.8 as well. But this is just doing it via the maths, where we do the inverse with that exact equation that we looked at before, and it's just filling in the blanks, basically. But again, we don't have to worry about this too much, and we're not expecting you guys to be experts in mathematics. So again, it produces the same output as before. Okay, so a few things to be aware of when you use things like linear regression is you have this thing called multicollinearity. Okay, so that's quite a long word, but effectively all it means is that multiple features are inherently correlated with each other. So you can have features that, for example, technically actually in context are very related, hence why they have very close correlations with each other. So what this means is effectively is that one of these features is redundant. You don't actually need that feature to be there to make your prediction. So this is one of the things that when you do machine learning modeling is knowing what data is actually needed for our training, and also then how to optimize, things like which features we actually need. Could we improve the model, this kind of thing. So for example, here we can use something like a correlation matrix. All this means is that we plot every feature against every other feature and produce the correlation between them. And we can just remove the highly correlated features because they are redundant. We don't need them because we already have a feature that is very highly correlated with that other feature. So they are basically the same. We can use PCA. So what this is principal component analysis. Again, it sounds very complicated, but it's not too bad. What it is that it takes a set of data and determines how many components exist within that data, i.e. how many features can we generate that describe most of that data. So if we had, because I've used this technique before, so I had something like 120 features in my data set. Now, that's a lot of features to have. So I was looking at, well, some of them must be redundant or I don't need them. So I run PCA and I can actually, bring that number right down to describe most of the data that I actually have. Again, use partial least squares regression is just another technique that can do this. So the main thing we're trying to avoid when we are training models is what's known as overfitting. So we're looking to, what overfitting means is that the model accuracy is great, it's amazing. But the problem is with that, it's actually deceptive. It's not actually as good as it sounds, because what's happening is that the model is almost like memorizing the data necessarily, rather than finding the best function that fits the data, if that makes sense. So imagine, if you will, let me draw a little chart somewhere in the corner. I'll draw it over here. So we have some data here that looks like this in some capacity, okay? And what may happen, so I'll change color for this so you can see it, is we want to find the best line that fits this data. Now, if we look at this with our eyes, because humans are very good at this kind of thing, we could actually draw a nice, almost like up and down curve like that fits that data well, okay? Now, what overfitting would look like, okay, is, if I go blue, it's a nice contrast, is that it's almost like going to every single point on this chart. So it would look something like this, like that. And the goal with machine learning and AI in general is we're trying to find the best general model of the data. So something like this wouldn't actually in reality be as accurate, even though by the metrics that you choose, it's actually scoring well. So the idea is we prefer to have the red line over the blue line here. Okay. So just to summarize this very quickly, what we're looking to do with linear regression is to find the set of weights for our linear function and for each feature. So the idea is we do this for every feature. So, we do the same process and find out the best equation for each feature compared to the target. And this is what's known as, parametric learning. So we're trying to find the best parameters for a function, which then models the data that we have. So this is a fairly standard approach, and it's what uses ordinary least squares. So this is effectively mean squared error. But again, we can have overfitting with this approach. Before I go on to logistic regression, I'll just check if there's any questions. So yeah, the randomness on that example equation is important, because if it didn't have that randomness, it would just be a straight line. So we're trying to find the best line that fits the data. So if we just drew a straight line, it just draw another straight line over it for that particular example. So I'll show you the actual lab sheet as well. So yeah, so all the algorithm I've used for all this entire section is just linear regression. So that's the name of it. So the line of best, it tells us if the data is good or bad. Well, that's a very interesting question. So data, I would say it's hard to know if data is quote unquote good or bad. It's more of a case of, can we model it well? So can we actually create a model that emulates that data well, or with the most accuracy? So if you change the coefficient, you would then get a different direction of your line. So going back to this one here, if we change the coefficient but kept the intercept the same, okay, so let's say rather than it being nearly 2, it was nearly 3, or 3 exactly, okay? So if we drew a line with that coefficient but the same intercept, it would start at the same point but go at a much steeper angle. Sorry, actually the other way around. Whoops. If we, let me draw another line in a different color because I can't see that. Sorry, if it was a higher coefficient, sorry, it would be a more shallower angle. So it would be more like this, okay? And so the coefficient would start the same. So let's say actually that this has a coefficient of 3. This one has a coefficient of 2. This has a coefficient of 1 in this case, okay? Let's just, for example, I know the scales aren't correct, but we'll go from there. What this would mean is that for this line here, the relationship between x and y would be 1 to 1. For this line, which is the best line that we came up with, it would be 2 to 1. And for this line here, the best, the relationship would be 3 to 1. So I hope that makes sense. So the coefficient just refers to how, when we draw this line, how steep it is. So it's what's the relationship between x to y. And all the intercept refers to is where does the line intercept with this y-axis here. So if the intercept was 2, the line would start down here. So I hope that makes sense. So what that allows us to do is draw a line in any direction in any part of the chart. Okay, so I hope that answers your question. Yeah, exactly. Similar to slope of the line. So, okay. So that's a summary of how linear regression works, but there are just a few other things that we can do with this to improve it. So obviously we have this tendency to overfit if we used least squares. So we can do, we can regularize the model. So effectively what that means is that we want to keep the most important features and then ignore the rest. So this comes down to, some features are redundant. You may have 2 features that are basically the same feature, just in a different perspective. And, we don't want duplicates because that can sometimes mess with the output of the model. So we want to regularize it. So how do we do this? Again, don't worry too much about the equations. I'll go through this. So we have a couple of different ways of doing this. So what we want to encourage is what's referred to as sparse models. Okay. All this means is that out of all the features that we have in the model, only so many of them are actually used in making the prediction. So we want the least amount of features possible that make a good prediction, if that makes sense. So rather than having tons of features, so if you duplicated a feature 100 times, it would dominate the model, as it were. So your prediction would always be based on that rather than the other features. You want the least number of features for the best accuracy, because that prevents overfitting. Okay, so the way we do this is, so this equation looks horrible, but I will draw a line here to explain what's going on. So this part here is just the linear regression we've just looked at. So you can effectively ignore this part for now. Okay, so what we do, however, okay, so remember that our total, so this is our mean squared error, sorry, and effectively, oops, I wish I had a drawing pad here. Okay, so we have our MSE here, and that's our normal equation for it. Now, what we add is what's known as lasso or L1 regression onto it. All this is just another number we add onto the end that encourages sparse models. So the way that this works is that effectively what we do is that we add up all the weights. So we just add them all up, which is what this refers to here. So we've got our weights, and this just refers to the sum of. We add them all up, and we simply add it to our MSE. So all this refers to is MSE plus L1 here. So this is just the sum of all those weights put together. So the idea is that the error will be higher when we have a lot more weights. So by including this extra little bit on the end, what's going to happen is that the solutions that are the lowest error are going to be ones that have the lowest sum of the weights, i.e. you're going to have some that are 0, which then means that they're not being used in the model. So I hope that makes sense. The next thing is we have ridge regression, or L2, okay? And it does a similar job. Again, it's exactly the same as before. I'll draw a line here. Whoops. This is our MSE from before. And here we have a regularization parameter. So effectively, we have a parameter that effectively shrinks the size of the weights as penalty. So we're adding on weights, sort of t here, so the target multiplied by the weight. So it's similar to the first one, but it just calculates it in a different way. And again, the idea is that it promotes that sparseness in the model. It does exactly the same thing. So there is a trade-off between these two methods. So lasso tends to work well if there are a few significant parameters and the others aren't significant, i.e. you've only got, say, a handful of features that actually matter to the prediction of the model. Ridge works well when you have many parameters, effectively, that are sort of hovering around the same value. But can we actually put these together? Well, because maths, we can in this lovely equation, which is effectively just, so where's my thing here? There we are, I'm here. So again, I'm just going to split this up. So what we call here is elastic net. Again, it's just a name, but what it refers to is it's L1 and L2 regression put together with MSE. So you have MSE here, then, oops, my mouse is going crazy. This is our L1 here, and then here is our L2. So I hope that makes sense. All we're doing is just adding them all together. So we create an overall error that is higher because of certain characteristics, such as, you know, having high values of weights, or, you know, in the case of L2, you know, we want to penalize, so we're dot producing the total weight amounts, and that then again encourages lower numbers of weights and therefore a more sparse model. Okay, so I hope that makes sense, guys. I'll just double check with you that that's okay. Yep, okay, so no other questions. Okay, I'll carry on. So again, this is just a summary. So we've got the three techniques we've just mentioned. We've got lasso, we've got ridge, and then elastic net is the two together. So again, you may choose one over the other depending on your circumstances. Let's say you have a large data set, but you're only interested in finding out which ones are the most important features. You then may prefer to use lasso in that case. And ridge is more preferable when you have a lot of parameters that are needed for the prediction. So that's where that might be useful. And elastic net does both, so it may be the case that that might be preferable. Again, this is something where we do something such as what we refer to as hyperparameter tuning. So that sounds quite scary, but all it means is that we're finding out what's the best settings for our algorithm to produce the best result. Okay, so that's the overall summary of linear regression. We find the weights that best fit a linear model to some sort of data that we have. We use mean squared error for it, and it can work with a large number of features. We can use other methods of training, and again, we have other strategies that can help make the model better. So these are things that have come up over the years to make things more robust. So I hope that makes sense. Cool. I'm just like to double check there's no messages. Okay. Now, logistic regression. So this is slightly different, but the principle is the same. So what we do here is we want to use a similar approach to do a classification problem, i.e. we want to be able to decide whether something fits into a group of, say, true or false. So effectively, something's either going to be 0 or 1, or true or false in this case. Okay. Now, can we use linear regression in its current form to do that? Not strictly speaking, but we can do it if we change what function we're optimizing for. So the way this works is we can use something known as a logistic function, or also known as sigmoid, and it's represented here by this Greek symbol here, which I believe is sigma male, and this is what's used to represent sigmoid function. So as we've seen before, this line here, this sort of dark red line here, refers to, so this one here, refers to a linear line, okay? So what we're expecting to produce here is this gray line here. So we want something to be either 0, and then it changes to becoming 1, okay? Because we want it to be either true or false. So if we use a regular linear line for this, we can't really do that because it doesn't really fit with this. There is a cutoff point and then it turns into, it's either 0 or 1. However, what we can do is we can use a logistic function which has this S-type curve. So notice how if we change the parameters of our logistic function here, which are these 3 lines here, okay? So we start off with 2x, 1x effectively, or just x, and then x over 2, we actually change how strong this S curve is. And a logistic curve will always start and end at 0 and 1. Okay. So what we can do here is we notice here out of these three, which one's the closest to this step here. And obviously I would say the red line, because that has the coefficient of minus 2x. So, and notice how it's an S curve here. It doesn't quite reach this cutoff point, but there's a very narrow window from about here to here where it actually transitions from being 0 to 1. Okay. Now, how can we use this to do the classification? So what we can actually do is we can use this to act as the probability of an example being either true or false. So if you treat this like probability, then what we can say is if a data point is, for example, has the x value -3 here, and let me just change the color so it's a bit easier to see. Okay, has the value -3 here, and we're assuming our function is this red curve here, so it lives here on the line. We know it's going to be -3, our x, and based off this curve, the probability that it is, either 0 or 1, it's going to be 0 here, because that's where that will intersect with it. So that's our line there. Okay. Now, if it were, let's say, our value is 2, we can then see it would intercept here. So the chance there would be the chance of it not being, the chance of it being true in this case is near 1. So it's nearly 100%. So that gives classification, as it were. So I hope that makes sense. So I'll explain this a little bit more. So when we train this, we use a different approach known as gradient descent. And the way that I like to think about this is imagine you have a set of hills, okay? And the hills represent, say, the amount of error that you're going to get with your function. And the idea is you want to get to the lowest point on all those hills as possible. So sometimes you may get, a drop, and then it can have a local dip, and then it will peak again and come right down to the actual true base of those hills. And the way we do this and how gradient descent kind of works, it's almost like rolling, a ball down the hill, as it were, and basically watching where it ends up. So every time you tweak the parameters, is it lower down the hill? Yes, then we will move further. Then we'll carry on in this direction. So it comes up with the best direction to go with doing that. So I hope that makes sense. Okay, so so how do we actually make a prediction with this? So if we have this S curve here that we had before, how do we actually make a prediction with this? So one way to do it, and this is the way that it actually works, is that we assume anything over 0.5 here, which represents 50%. 50%. Oh, my mouse is having a wobbler today. Anything over this 50% is going to be categorized as 1, and anything below this 50% will be categorized as 0. So that's how we make a prediction with this, because if we're treating it like a probability, if it's over 50%, then in all likelihood it's going to be 1, and or true in this case, and if it's below 50%, it's likely to be false/0. Okay. And again, this is just summarized in this equation here. So our sigmoid here, i.e. our sigmoid function of the weights and our x data, if it returns a value greater than or equal to 0.5, we can say it's true. And if it's not, if it's below that, we can say it's false. So I hope that makes sense. Again, this is just a representation of how that looks. So our probability, so P, is our sigmoid, our weights, multiplied by our data. And then our final Y value, okay, is going to be either 0 if P, in this case, is less than 0.5, and it's going to be 1 if probability is over 0.5. Does that make sense, guys? So I hope that's fairly clear. What we do if it's exactly 0.5? Well, the equation shows here that if it's equal to 0.5, it will actually say it's true. So that is, yeah, exactly. Yep, so logistic uses probability, yep. I apologize if this is too much maths, but as I said before, the goal here is that we do not expect you guys to be maths experts. The benefit of going through the maths is just to give you guys a better understanding of how these algorithms work. So obviously when we go through, for example, the impact of AI module, we talk about the trade-offs of different algorithms and why certain ones are better than others. And sometimes that can be explained through the mathematics, but it's not necessary. Okay. There are a variety of things like books and YouTube videos and things like that explain this as well. So for really doing this practically, you don't need to know the in-depth of the maths. Yeah, the way that it does the prediction is rather interesting. So effectively, what we do is we have a weight for each feature. So imagine if this down here is our feature. So I'm just going to put an F here. Okay. And our prediction or our probability here is this side, so P. The idea is that for a given feature value, so if it were 1, for example, we've modeled it to be this S-curve. So what this will then say is the probability of when that feature is equal to 1, the probability of this case or this example in the data of being true or in the class is going to be in roughly here about 0.65 or something like that. So it's 65% chance, as it were, that it's going to be inside that class. And that's what these equations here represent. So we've got our sigmoid function, which is the blue line. We've got our weights, so those are determined by our training, and our x is our data point. And then if this, in this case, if 1 goes to here and it's 0.65, because it's over 0.5 or 50% probability, we're going to say that it's true, that it is part of a certain class. So I hope that clears it up a little bit. Yeah, exactly. Yeah. Cool. Okay. So carrying on. So how do we train it? So this is interesting. Okay. So we don't use mean squared error for this necessarily. So we use this log cost function here. Effectively, it does the same job as any other error function will do. So based on the training label or our true value, so our true value is either going to be 0 or 1 because it's either going to be in that class or it isn't. And what we're going to do here is for a given weight for our line, for our logistic function, the cost of it, so C, is going to be equal to these equations, so minus log the probability if the actual value is 1, and then log 1 minus, because it's the reverse, when y is equal to 0. So all this does is it calculates if this is wrong, this is the given error, because it can either only be 1 or 0. So I hope that makes sense. But again, it's not too much. We're not expecting you guys to fully understand exactly all of this. Again, going through some statistics is always a good exercise for doing machine learning, and we do cover some of it. But obviously, it's not necessary to go in super depth about it for at this stage. Okay, and again, this may look a little bit scary, but again, that's the equation we saw before. So we just calculate cost. And if we do across so many training instances, so we need to repeat this cost calculation n number of times. And that's all this means here. So this giant E here, or is the normal Greek letter sigma, this just means the sum of. So we're doing this piece inside here n number of times. And the idea is then we adjust the weights every single time as we get closer and closer to the best or most optimal values. I hope that makes sense. Okay, So again, we're looking to minimize the weights. Again, we use something called gradient descent to do this. So what's going to happen is if I draw up here in the corner, just for now, I have imagine this is our problem space, okay? We have this curve that represents the error, okay? And finding the best weight, so we've got error here, E, and the weight. So the best weight we want to find is where the error is the lowest. So by that logic, looking at this curve, we want our weight to be all the way down here somewhere. So because that's got the lowest error, so the weight value would be some arbitrary value there, okay? Now, the way we do gradient descent, again, we don't have to go into super detail about this because this is going to be part of the neural networks discussion, but I'll give a very brief, very high-level view of it now, is imagine we choose a random weight to start with because we have no idea what is a good weight. So let's say our random weight ends up on here on the curve, okay? Now, we work out what our error value is here, okay? And then what we do is we choose another random weight. And let's say it's down here, okay? And our error is slightly lower than the first time. Okay, so that's our first one, and that's our second line. And you'll notice that the error has gone down. So I've drawn a little arrow there. Now, what we do is between those 2 points, we draw almost as it were the direction in which the weight is going. So in this case, if we choose, we can see that we're going in the correct direction. So what we then need to do is, that means we need to keep increasing our weight value because this one was here, and then when we increased it to here, the error was lower. So if we keep increasing it further, our error will continue to come down, which it does. And then you repeat this n number of times until you end up residing at some kind of value, such as at the end here. So I hope that makes sense. So it's almost like I say, you're rolling a ball down the hill and you're wondering which direction the ball is going, and that tells you what in this case, the weight value should be. Okay, so how do we actually do this? Right, so this is all part of the lab exercise or the lab notebook. So what I'll do is I will go straight over to the collab for this because this is exactly the same as what's on the collab. So I'll just jump over to that. No, I do not. So I hope that makes sense, guys. Yeah, so I'm going to.
Luke, before you
Yep.
start the now the lab, I just wanted to ask you that the train continued equation that is predefined in the machine learning algorithm. We just have to use that library, and we just have to put our values, and it will automatically pull out the trained.
Exactly, yeah. So you don't have to
So
do anything.
yeah, we
Yeah.
just in case when we are going for the placements, and what if they ask us how we derive that equation? So we're supposed to know that the behind part of that equation. Is it necessary to know all those behind part of that all the equations in AI, like the
Um,
all theoretical basis?
no, it's not necessary. And from my experience, generally speaking, so long as you understand, let's say, the trade-offs between each algorithm. So you don't have to necessarily understand how they function at a, mathematical level. It's just a case of, okay, I know linear regression has a tendency to overfit. That's kind of the thing that if people question you on it, that's the kind of thing they look to know and see that you do know. But that's it really. So like you say, all this mathematics is included in the libraries, so you don't need to actually rewrite any of this. But the idea is just that we still go through it anyway, just because it's good to just have that understanding, and it can be helpful in understanding, well, why does linear regression overfit, for example? Why is that the case? So I hope that makes sense. I hope that answers your question.
Oh yeah, of course, definitely. Thank you.
Cool, no worries. Want slope at given point to be 0 for logistic regression. So the parameters for the logistic regression basically determine how the angle of that S-curve, effectively how sort of tight or loose it is, and that depends on the data. So if you have a bunch of points that fit within this, so let me actually quickly draw an example on the thing just to explain how it actually does the prediction and training from this before I go on to the Colab book. Okay, so let's say we have some pointer options, pen. Okay, so we have some example, I'll change the color to one that isn't on here. Okay, so we have some example data points. They're either going to be 0 or 1, okay? And they're going to be, say, here, 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 and they're going to be down here somewhere. So they're only ever going to be 0 or 1, okay? And the idea is we sometimes have some overlap where, for example, there might be some cases where, given this X variable, the value is different. So it can be 0 or 1, depending on, because this is, real world data. You have very different, people can be, for example, one thing we've looked at during the course is predicting if somebody is going to have a stroke, for example, and the data for that, you do get overlap. So this is where classification models, when you analyze them, you look at that kind of overlap and see which ones are getting right and wrong. So basically what we're looking to do is draw a S line between these two here, okay, that fits as close as possible and gets these examples as close as possible. So for example, if our feature down here, our X, is this one here, so it's like, minus 3 point something. Does this S-curve fit that because it is class 0? Yes, it does. So we know that that's going to be a good prediction. Now, where things get interesting is towards the middle. So this one, for example, where X is just below -1, now this is where the probability starts to change. So the chances of it being 1 in this case is only 0.09 here or something like that. Okay, so like 9% chance that it's going to be 1 or true. And similarly, but this one here, we go to this red line and we go across here. This example, again, it's going to be 0.3, or something like that. And then what happens here is, let's take this example here where X is this. If we take it all the way to that red line and come across, what it's actually going to say here is that it's 0.65, so a 65% chance that it's going to be 1, even though the real value is 0. So again, this will be an error. So if we do this for all of these, and we go by this line here, so these ones, because they'll be over 50%, there will be 1. So we've got 4 here that are correct. We have these 5 here that are correct, okay? But now we have these 3 where this one, for example, has become 1, even though the probability of it being 1 is only, 0.1 or something, or 10%. So out of this sample data, we have 5 plus 4, so that's 9. And we then have 3 here, so this one and these 2, that are incorrect predictions. And that's how we calculate the error. So we can then say, okay, out of all these samples, how many of them were right and how many of them are wrong? And that gives us our accuracy for this particular instance. So we're saying it's 9 out of 12 in this case. Whoops. 12 in this case. Okay, so 9 of them were correct out of a total of 12, which works out at 75% accuracy. So that then becomes how accurate this model is. So I hope that makes sense. I know it's very doodly on the screen, but yeah, I hope that made some sense. Okay, cool. So I'll quickly go through the book because I know we've run over slightly. I'll go through this very quickly. And okay, so reconnect. So what we have here, this particular notebook, so this is part of the the materials that you guys should have access to. And it's a very simple notebook, so there's no real tasks per se inside of it. It's more so the case of observing how we actually use linear regression and logistic regression, for example. So just to explain a little bit some of the Python code, because I know some guys have been struggling on that, or it seems confusing. Again, we're not expecting you guys to be, expert programmers at this stage. So what I'm doing here is this is just dependencies. So this is like, what are the libraries that we need to do this? And all I'm doing here is telling the server that the Google Colab runs on to install these things for me. So pandas, NumPy, Matplotlib, and sklearn. Pandas deals with manipulating data. NumPy is a mathematics library. Matplotlib creates nice, pretty charts. And sklearn actually has the machine learning algorithms inside of it. So if it's got an exclamation mark here, what I'm doing is asking the server to install this for me, and pip is the name of the Python package installer software. So that's just dependency stuff. So coming to here, our first piece of actual code, what we're doing here is we're saying, I want to import something from sklearn. So sklearn is a library that deals with machine learning. It also happens to include a load of ready-made data sets for you to use. So in this case, I want to import a data set which is called load wine, or this is a wine-based data set. I then create a variable called data set, which is equal to my wine data set I've just loaded. And then I tell it to give me the feature names in that data set. And as you can see, there's a bunch of features in that data set. There's the percentage alcohol, malic acid, ash, magnesium, blah, 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 stuff I don't understand to do with wine, etc. Okay. Then we move on to some things that you guys may have seen already, which is, so I'm importing pandas and I call it PD because that just gives me a name I can use to do data manipulation with. And I'm creating what's known as a data frame. This is just a thing to do with Python that lets you manipulate data effectively. It takes that data set and turns it into something you can manipulate. Going on from there, so the data set itself includes some target classes. So as we mentioned before, it can either be true or false, depending on which class it is. And in this data set, we actually have 3 different classes. We have 0, 1, and 2. So effectively, these are different types of wine that exist inside the data set. And if I do dataset.target here, it gives me the list. So in this case, an array, it gives me all of the classes for each sample inside the data set. So for every row in the data set, this is the class that it was. So in this case, 0, this might be white wine, for example. 1 might represent red wine, and 2 might represent rosé wine or whatever. I'm not really a big wine drinker. So, so these are our 3 classes within this data set. What I'm going to do now in this notebook is we import a couple of things. So from sklearn, so remember sklearn contains everything to do with machine learning. We want to import something known as test train split. So this is a function that lets us split the data set into nice chunks so that we can train the model and then test the model against it. So when Ian mentioned before about you keep some of the data back to then test it, that's exactly what this does here. So again, you don't have to do that. There's stuff built in that does that for you. And I also import the metrics from sklearn so that I can use them later for now. Okay, so going on to some of the other stuff. Effectively, again, I'm importing NumPy here, a mathematics library, and Matplotlib, which is again, creates pretty charts. And here I'm going to create a series of points, and these are just random, okay? And we're plotting them using the equation that we saw inside the presentation, which is 2x plus 3 plus some random value. And we get the data that we saw before by generating this chart using this dot scatter, and then I put the data in. Now here's where we do the actual linear regression. So what we have here is exactly what we saw in the presentation before. I'm importing from sklearn a linear model called linear regression, because this is what we want to use. I then create a regressor, or it's just called RGR in this case, and that is going to be equal to linear regression because that's what I want to use. I then tell my regressor I've just created to fit to our X and Y data that we have from our wine data, from our randomly generated data set here. And I create a scatter plot, which is this background here. And then what I do here is draw the line over it. So what I'm doing to get that line is, so I know what the X is going to be because the data only goes from 0 to 2. And I can create that using this range function. All it does is it returns a list, which is going to be 0, 1, 2, because it doesn't include the 3. It goes up to 3. So that means then I've got 0, 1, 2. Okay. And then what I have is I use the coefficient from the regressor that it's worked out and the intercept, and I can then plot my line of best fit. So I hope that makes sense. So this is exactly what was in the slides before. And again, I print out at the bottom the coefficient and the intercept. So again, it's roughly the same as what we saw before. It's just over 3 and the coefficient is nearly 2. So going over to logistic regression, this is just a bit of code, so don't worry too much about this, which generates that nice chart we saw before. This is the code that was used to do it. So there's nothing to worry about here in terms of understanding how this works. It's just a case of how they generated this plot, and basically each line here is each of these lines that they drew. Now, actually getting to using logistic regression, so this is the actual important part, it's exactly the same process as linear regression. We're going to import, so they include logistic regression under linear model in sklearn. So I'm going to import logistic regression. I make a classifier that I call CLF, and I'm going to use logistic regression, of course. And my max number of iterations, so this is the amount of times I run that training process, I'm going to do it 10,000 times. Okay. Exact same thing as before with the linear regression. I'm telling my classifier to fit to the X training data and the Y training data that we created earlier. And then I make a prediction. Okay. And how I do that is by telling the classifier to predict using the X test data that we've kept back. And then the accuracy is calculated using sklearn's metrics. And I create an accuracy score between my prediction that I've created here and the real Y values that we hid earlier on. And then all I'm doing is printing off that accuracy. And if you look at the accuracy that's generated, it's 94.4%. So similarly to what we looked at just on the slides, where you have some samples that are 0 and some that are 1, what's happening is that out of all of those samples that were put onto the curve, as it were, 94% of them fell in the correct class that they were meant to be in. And the way that this works for when you have multiple classes, like in this case where there's 3 classes, is that if you imagine a logistic curve for each class individually, so each class has a separate logistic curve. And again, what we can do here is we can look at the coefficients and the intercepts for each of these. I've rewrote this a little bit here just to make it a little bit clearer. So for class 0, again, this could be white wine for all I know. We've got all the coefficients for each feature. So for every feature, we have a different coefficient. And then we have the intercept for the overall logistic curve that was created. And we do this for every class. There is a separate logistic curve and separate coefficients for each one. So again, this, and that's it for the lab sheet. So this lab sheet isn't not asking you to do anything in particular, but I would recommend playing around with it. Potentially, if you find some other data, for example, from Kaggle. So if you guys have used Kaggle before, you can go and get data sets for free off there. It's really nice, super simple to use. you know, they have all the different topics. So I can choose various things like education here, and I can go and download, for example, a student performance data set. I can then take that and use it, you know, perhaps train a regression model, something like that, or a classification model to predict grade or something like that. So again, like I said before, to keep up, you know, keeping up with AI stuff, doing stuff like this is good fun, and it can just sort of help. The more you practice, you know, the easier it becomes. It is definitely a practice skill. Again, like I said before, you don't need to know all the ins and outs of the mathematics to do this well. So again, we're not going to force you guys to study maths for a year. So don't worry about that too much. So yeah, I'll answer any questions. I'll stop sharing my screen there. I hope that made sense, guys. Yeah, does anybody have any questions? Yeah, maths is fun. Yeah. Good. Excellent. Cool. So yeah, so what I'll do is, if there's no other questions, I'll stop the recording here. But if anybody has any other informal discussion they would like to have with me, then I'm more than happy to do that, about like my experience or what have you, for example. More than happy to do that. So I'll stop the recording now.